Okay, so with this bell work is really just kind of a conceptual question related to what we started talking about yesterday. And the basic idea is it's results from baseball games. There's the runs scored against you and the runs that you scored as a team. And, you know, more points wins, more runs wins, I should say. So basically the only thing that I'm expecting of you guys is to be able to recognize that a perfect 1-to-1 right here is showing ties where both scores are the same. So you just need to determine which side of that line means a win and which side of that line means a loss. Well, on this side down here, the runs against is greater than the runs scored. So these are all losses. On this side, the runs against are less than the runs scored. So these are all wins. So if you count that up, it's 12 and 4. The correct answer is D, which is what most of you had. So that is good. Okay. And just one thing I wanted to show real quick, and this I will get out of the presentation. To do this, we were talking about correlation is not causation. And I just wanted to give an extreme example, which is kind of humorous here. There's a website. It's Spurious Correlations. If you look that up, you can find this. And we're going to look at some things that correlate very strongly. U.S. spending on science, space, and technology correlates with suicides by hanging, strangulation, and suffocation. And look at that R value, 0.9978. All right, so if we look down, this one's fun. Number of people who drowned by falling into a pool correlates with films Nick Cage starred or appeared in. And that's got a pretty strong correlation. It's 0.666. That's a pretty good one. Per capita cheese consumption correlates with number of people who died by becoming tangled in their bed sheets. And I was looking at this earlier. This one is shocking. We have up to over 800 deaths of people getting tangled in their bed sheets. And I'm not sure how that's exactly determined. But anyways, that is way more than I would have expected. But that correlates very strongly, 0.947 correlation coefficient there. So of course you can see there's lots of these. I'm not going to show you all of them. If you want to look this up, you can see all these spurious correlations that show things that correlate that there's no way that one causes the other. And anyways, just kind of a fun little aside there. So chapter 8, we are dealing with linear regression. That's the name of the chapter. That's what we're talking about here. And you can see we're starting off talking about linear models. And the scatter plot itself, we talked about that yesterday, and we can describe it with Duff's. Hopefully you remember all that fun stuff. But really, kind of the takeaway for scatter plots a lot of the time is creating a model so that we can predict values. Okay, so on this, I'm just showing this model to show the where the model would fit. And don't worry about these numbers so much. We're going to go through a lot of conceptual stuff, but at the end of class, we're going to tie it together and do some actual practice problems finding regression equations. Okay, so the line of best fit is specifically what we call least squares regression line. And we'll do this little demonstration why it's called least squares. Okay. So the first thing I'm going to do when we get over here is we already have a line, or a least squares regression line that's shown, and I'm going to get rid of it. And I'll get rid of all this stuff for now. Okay, I want to show this. But anyways, I'm going to move these points around just to make it a completely different correlation going on. I'm trying to make it where it's going to be tough. Like this one right here, I honestly look at it, I don't know. There's not going to be much of a correlation here. But, you know, maybe this has, I'll just guess right here that maybe this is the best trend line through it. I don't know, that seems off, but maybe right there. So it doesn't really matter for right now. Wherever I think it is, for right now, the difference between all these are residuals. And we're going to talk about residuals a lot more tomorrow. And what I can do is I can take these residuals and I can actually square them. And so this is literally squaring them by turning them into squares. And the whole idea is we want to find the smallest total area of all of these squares combined. And once we find this, the lowest possible sum of squared residuals, that is our line of best fit. That's our least squares regression line. So least squares, that kind of explains it all. So right now, the total sum is 471. And I highly doubt this is going to be it. But notice when I move this around, the sum changes right here. And as I move this around, lowest it gets is about 469. Now I'll just try and move this side. If I do this, it gets down to like 461. I'm only going to do this a few times. Here's 458, seems about the best right there. 457. I'll just do this one last time. And now what I'm going to do is I'm going to turn on, because it's already been calculated in this demonstration, I'm going to turn on the least squares regression line. It's going to show up as a blue line. So there it is. I got pretty close to it. If I had been right on that, 456. That's about as low as I can get. Okay, so we're going to come up with this least squares regression line, but we are not going to go through it in this process. We have a much, this is somewhat complicated. We have a much simpler way of figuring this out. So that's what we're going to be talking about today. But it's just important to understand conceptually that we are minimizing, so you can imagine almost like a parabola of values. So we want to find the vertex at the minimum of area. So that is the whole idea. So the process, we are going to square the residuals, find the sum of the squared residuals, and the line that results in the minimum sum of squared residuals is the least squares regression line. Pretty straightforward. Okay, so just a little bit about residuals. I'm throwing out y hat right here. We're about to talk about that. The predicted value is if we have a good residual or a good least squares regression line and we have a very high correlation with our data, then you might not have much of a difference between the predicted value and the actual values. But there will almost always be a difference, and that is called the residual. And you can see you take the actual data point, you subtract what the model predicts, and that's your residual. Okay, and again, we're not going to focus on that a whole lot today, but it's worth introducing. So if the residual is positive, then the model underestimated the true value. So like here with this d sub 1, this is the actual value minus the predicted. This is going to give us a positive number. That means there is an underestimate here. This one right here, d sub 2, the model is above it. So when we subtract the actual minus the model, then we get a negative residual, and that negative residual means that there is an overestimate of the true value. So it's kind of a little counterintuitive, it's backwards. If it's positive, it's an underestimate. If it's negative, it's an overestimate. And sometimes I had to like think through that in my head and kind of visualize a diagram, a scatter plot to make sure that's clear. So again, that's going to be something we talk about a whole lot more tomorrow. So anyways, this is the actual least squares regression line equation. And that is y hat equals a plus bx. Also, it's written as y hat equals b sub naught plus b sub 1 x. And this is what your textbook has. This is what your calculator will kind of have it as. And a lot of sources use A and B. It doesn't really matter what letters we use here. But bottom line, in this case, A or B sub naught is your y-intercept. So you can see they're in the same relative position. B and B sub 1 are going to be your slope. And this is backwards from, now this I hope is incredibly familiar to you with the slope-intercept form of a linear equation. So if you're thinking y equals mx plus b, it's the same thing. Statisticians just switch it up a little bit for their own reasons, okay? And we just rearrange the slope-intercept form of an equation. The one thing that's a little bit confusing is that now b is your slope, and we are conditioned to see b as the y-intercept, but you're just gonna have to retrain your brain for this class. And if you study statistics in the future, you'll probably just start thinking of b as a slope or b sub 1 or whatever variable you use. Okay. So finding the regression equation. There's one property we need to understand from the beginning. Every least squares regression line passes through x bar, y bar. And the other way of thinking of that is every least squares regression line passes through the average x value and the average y value. We'll talk about why that is in a minute. But that's a good starting point. It's good to know that. What does that mean for the rest of the regression equation? Well, we will calculate that. But before we go through and calculate everything, we're going to kind of look at it from a conceptual point of view. This is from your textbook. So if this explanation, you're still a little fuzzy on it at the end, I encourage you to read those chapters again. Read that chapter again and that part of it specifically. And 173 to 174 has a lot of it, but you might want to start from page 1 of the chapter. Anyways, I will kind of do a brief run through. So I'll go back real quick. This is a scatter plot showing grams of protein versus grams of fat. So the idea is that this person thinks that there's a connection between the amount of protein that's in a Burger King menu item and the amount of fat. The scatter plot, it shows an association of some kind. And of course, we have residuals. We're not going to focus on the residuals so much right now, except that we're going to try and minimize that, like we already talked about. Now, one way of thinking about this is to standardize all of our points. That is, turn them into z-scores. So that's what we have here. Notice it's the same essential scatter plot, but it's been transformed. It's been shifted and rescaled. And now we can see it's the same essential shape, but now we've got z-scores for every point rather than the actual grams of fat and grams of protein. So what's important to note about this is that in the next page we talk about this. When we standardize this, the least squares regression line will always pass through 0, 0. So remember, z-scores, z-scores they reduce everything down to a normal model. And in the normal model, the mean is 0. So I can think about the normal model for my x values is just going to be x bar and then 1. And then for the y, it's going to be y bar. And 1 is a standard deviation, but both of these are 0. Okay, because in a normal model, they're both 0. So that's why we know that it's going to pass through 0, 0. And that means in a non-standardized graph, it's going to be passing through x bar, y bar. So hopefully that logic follows. Okay, so that's good. Now we need to think about the slope. And the slope here is given by this equation. So it's going to be an important equation. And these values, S sub y and S sub x, are the standard deviations for the y and the x values, respectively. And a lot of times those are just given to us. So if that's the case, we just plug that in and we can figure out the slope. And keep in mind, because this is a standardized scatter plot, all the standard deviations are 1. So I'm plugging those standard deviations in, but the standard deviation of y is 1. standard deviation of x is 1. So the slope here is just going to be the correlation. And in a standardized plot, that's all it is. It's just the correlation. But of course, we're not working on standardized plots, and we need to figure out how to get this on the real graph, which it's just this equation. So we already have the means to do that. But you can kind of see what's going on. Okay, so I'm going to bring everything up. Otherwise, this is a little bit confusing. So if we're going back to our non-standardized scatter plot, we'll simply use the formula given right here to calculate our slope. And this is going to be our starting point. We're going to start by finding the slope and then find the y-intercept. The slopes here, I should have changed this, not the slopes, sorry. The standard deviations are no longer 1. So we'll have to do some relatively simple math. And I've already done the math on this page. I'm not giving an example like step by step just yet. But so S sub y, remember that's saying that the standard deviation for our fat is going to be 16.4 grams. The standard deviation of our protein is 14 grams. So I just plug those numbers in over here on the right. You can see the slope is r times S sub y over S sub x. I didn't ever show it, but the correlation was 0.83. So that's important to know. So notice it's just been plugged in. R gets plugged in right here. These two get plugged in right here. And we can do the calculation. So we're basically just scaling the standardized slope to what it should be for a non-standardized scatter plot, if that makes sense. And once we've got it, we have a slope. And notice the units of our slope. It's grams of fat per gram of protein. All right, so we have both of our variables being represented in the slope. And that's going to be important when we interpret our least squares regression line. And I'm going to pause right here real quick. I've been talking a lot. Are there any questions? Okay. So we're going to look at kind of what the full calculation should be. So imagine, and you will have problems like this. So if this is given, where you have all of your information, and it's, you have X bar, Y bar, standard deviation of X, standard deviation of Y, and your correlation coefficient. If you have all that information, then you can figure out your slope, and then all you need to do is you can plug in a known point into your equation to solve for the unknown y-intercept. So this goes back to the very first thing we talked about. We always know that it passes through X bar, Y bar. So I'm going to take my X bar, Y bar point, and I'm going to plug that in because I know that's going to pass through the line. So notice that's what I did here. X bar and Y bar are substituted right there. And I went ahead and substituted the entire slope equation for B and redid that calculation. But you know, if you already solved for it, you don't need to do it a second time. But just in this example is what I did. Okay, so the actual Y bar is substituted right here. Notice 23.5 is our Y bar. 17.2 is our X bar. So that was substituted in. Correlation and standard deviations are plugged in. This is just letting your calculator do the work now. And when you do all this, you're going to get a y-intercept of 6.8. Okay, and this is all well and good. Questions on that idea? Hopefully this is making you think of Algebra 1 type stuff that you've done. So it's not like brand new math that you're having to learn. It's just notation and where do we get the information. Okay. So if I took that, we got 6.8 as our last result, 0.972 is the slope. This would be our model, but remember, this has context. So we want to show the equation with context. Anything, and I kind of skipped over this before, and I meant to say it and I didn't. Anything with the hat over it means it's a predicted value. It's kind of like when we learned that anything with a bar over it is an average value. Well, anything with a hat over it is a predicted value. Okay, so what I can say is the predicted fat right here is going to be 6.8 grams of fat plus, and now here's where we have that weird unit for this, 9.972 grams of fat per gram of protein times whatever input x of grams of protein. There's different ways you can write this, but you just want to make sure that the context of the problem comes through. And I wanted to have this example like really clearly spelled out, so if you needed to come back and look at this presentation, you could kind of see the full process of it. But in practice, you don't need to spend tons of time on all these individual parts. Hopefully you can go through these problems pretty quickly. So the last little bit right here is how to interpret this, because this is going to be one of the most important things. I mean, it's great to come up with a regression equation, but a lot of times they're going to ask you to interpret what the slope means or what the y-intercept means. And that, I can almost guarantee you will see a question like that on the AP test. So here's what we might say. To interpret the slope, you could say, according to the model, for every additional gram of protein in a Burger King menu item, we would expect 0.972 grams of fat added also. It's a positive slope, so that means as one is added, another is added, and we calculated, it's almost 1-to-1, 0.972. Okay, but that's adding the context and it's showing that we understand exactly what that slope is meaning. So any questions on the slope here? Okay, and remember when we say for every additional gram of protein, that is the denominator. For every one of these, we get 0.972 grams of fat, which is our numerator. Because remember that our slope is our change in y over the change in x, and our change in y here is 0.972, our change in x is 1. So again, going back to algebra 1 type stuff with that. Okay. Now we've got the y-intercept. To interpret that, and now we're only talking about this number here. I don't care about the rest of the equation, but I might say in a menu item with 0 grams of protein, our model would predict 6.8 grams of fat. Okay, straightforward. All right, so that's interpretation. Just one example here. Look at other examples in the book, double check your work as you're going through. If you have questions, of course, let me know. So what we're going to end up with today is I just wanted to look at a couple of problems. And this is where we tie it all together. So we're comparing homework grades to test grades. You don't see the scatter plot. Honestly, it doesn't really matter because we have all the information we need. So let's just say we've got X bar, standard deviation of X, Y bar, standard deviation of Y, and the correlation between the two. So we need to figure out what is our regression equation. Okay, and at the beginning I should point out that these two are homework, because what we are doing is we're predicting test grades based on homework grades. And of course, remember your correlation is symmetric, so it doesn't matter which one we're correlating to which one's X and Y. It's gonna be 0.76 either way. Okay, so let's now kind of start with this idea. Y hat equals A plus BX. And I'll worry about the context at the end, but for now I'll just use the generic symbols. Okay, so I want to start by finding the slope. I have everything I need to find slope. I just need to remember that slope is the correlation times the standard deviation of Y over the standard deviation of X. And those were given to us. We can figure that out really quickly. So my correlation is 0.76. The S sub Y is 10. S sub X is 5. So I can multiply that through, and that reduces down to 2. So it's just 2 times 0.76, which should be 1.52. Again, we'll worry about the full context at the end, but we're basically saying, homework, or no, I'm sorry. Oh, I didn't want to do that. That was bad. Here it is. Okay, so this is going to be points for a test over points per homework. All right, and this gives us y over x. Okay, so let's come back over here. Y hat equals a plus 1.52x. And now this is where I need to remember that one point that passes through every single regression equation, every regression line, is x bar, y bar. So I'm going to take this value here and this value here and plug it in for my x and y. So y bar equals a plus 1.52 x bar. Plug those in again. So y bar is going to be 74 equals a plus 1.52 x bar is 84. So now I can plug all that in, and so when I plug that in my calculator, I got negative 53.68. All right. So that's a weird y-intercept, but that's what we got. So let's plug this now in, and our regression equation is y hat equals negative 53.68 plus 1.52 x. And if we were just trying to do some calculations, that's all we need. We need to make sure we have the context. So I am going to now rewrite this with some context. So I'll try and squeeze this in. I might actually erase this, give me a little bit more room. So test, the predicted test value is going to be negative 53.68 test points plus 1.52, and this is going to be test points per one homework point, times, and that's right there, is times x number of homework points. And there it is. Okay, I know you guys just are listening to me. I apologize, that's how this goes, but there's a whole lot to cover. I want to make sure that we have time for it all without keeping you here too long. So anyways, that is the regression equation. So now we have one other question. What test score would you predict for someone with a homework grade of 70? As soon as we have the regression equation, then it's just as simple as plugging in for x. And here is, all we have to do. I'll just go back to this equation right here. So my predicted value is just going to be negative 53.68 plus 1.52 times 70. And once I plug that in the calculator, let that do all the work for me. You can plug the numbers in at home. And see if you get the same thing that I do. Okay, and there it is. 53% basically is what we might expect someone to earn. So I'll tell you, this is the more time-consuming way of finding a regression equation. I can show you, and it depends on how they give you the information. If they only give you those 5 summary statistics, then we've got to use them. We got to go through this process. And are there any questions on this process? Okay. It's actually, believe it or not, a little easier when they give us just a data table. Because at this point, our calculator can do all the work for us. Okay. Now, I do believe there's a way of using your calculator even in the other way to make it go a little faster, but actually, I'm not sure if it makes it any faster. So let's just look at this. The first thing that we're going to want to do, well, let's just read it. The table shows a number of live births per 1,000 women aged 15 to 44 in the US starting 1965. It starts off asking us to make a scatter plot and describing the trends. That would be Duff's, make sure direction, unusual features, form, and strength. Find the equation of the regression line and check to see if the line is an appropriate model, explain. So let's just focus on that second part for right now. Plug that data into your calculator. And if you're done and you're waiting on other people, you can go ahead and create the scatter plot, see if a linear regression makes sense.